aspirants. This question is from GATE 2019, Mechanical Engineering paper, Set 1, question number 45. Two immiscible and incompressible viscous fluids having same densities but different viscosities are contained between two infinite horizontal parallel plates, 2 meter apart as shown below. The bottom plate is fixed and the upper plate moves to the right with a constant velocity of 3 meter per second. So this bottom plate is a fixed one while the upper plate is moving with a velocity of 3 meter per second to the right side. With the assumptions of Newtonian fluid, steady and fully developed laminar flow with zero pressure gradient in all directions, the momentum equation simplified to d square u by dy square is equal to 0. If the dynamic viscosity of the lower fluid mu2 is twice that of the upper fluid mu1, then the velocity at the interface, rounded off to 2 decimal places, is dash meter per second. So we need to find out the velocity at this interface. We'll start by writing the given information. Let all the properties of upper fluid be written with the subscript 1 and the lower fluid be written with the subscript 2. Here we have been given density of fluid 1 is equal to density of fluid 2, then viscosity of fluid 2 is twice viscosity of fluid 1. The height of the part with fluid 2, let that be h2, it is 1 meter given in the figure. Hence h1 is nothing but total height 2 minus 1, that is again 1 meter itself. Velocity of the top plate u top is equal to 3 meter per second, whereas velocity of the bottom plate u bottom is equal to 0 meter per second. Now after the assumptions are applied to Navier-Stokes momentum equation, we are being given the simplified momentum equation, which is d square u by dy square is equal to 0. Now our aim is to obtain velocity profile u, because we want to know how the velocity varies in the fluid. So we will integrate the momentum equation. We get du by dy is equal to a constant. Let that constant be c1. Integrating it again with respect to y, we get u is equal to c1 into y plus another constant, let that be c2. So this is our velocity profile, which is linear. When velocity profile is linear, we have the shear stress tau will be constant throughout the depth. Because by Newton's law of viscosity, we have shear stress tau is equal to mu into velocity gradient du by dy. So clearly mu being a constant, if u is linear, tau is the slope and hence it is constant. Slope of a line is a constant value and hence tau is constant. So if tau is having a constant value throughout the depth of 2 meter, we can find out this value of shear stress, and that will be the shear stress at the interface. We can find it out from the top fluid as well as using the bottom fluid properties. Hence, using mu1, we have tau is equal to mu1. The velocity gradient here is nothing but change in velocity from top to bottom, that is 3 minus, let the velocity at interface be v. 3 minus v upon the height is 1 meter. So 1. This is equal to mu1 into 3 minus v. Similarly, using mu2, we have tau is equal to mu2 into. Now the velocity variation here is from v to 0 and the height is 1. So we have mu2 into v. Now we can equate equations 1 and 2 as the value of tau is same at the interface. So we have mu1 into 3 minus v is equal to mu2 v. We can put mu2 in terms of mu1. So mu1 is into 3 minus v is equal to mu2 is 2 times mu1 v. Mu1 will get cancelled on both sides and we have 2v plus v is equal to 3. This gives us velocity v at the interface is equal to 1 meter per second. So our answer here is 1 meter per second. The unit is already given and we have found the velocity in the same unit. To learn Newton's law of viscosity in detail, you can refer to the NPTEL video Module 1, Lecture 1, Introduction and Fundamental Concepts 1 of the course Fluid Mechanics by Professor S.K. Som, Department of Mechanical Engineering, IIT Kharagpur. I hope you understood this solution. Thank you.